Good morning, everyone. Let's welcome to the EM-X and the 25-26 academic year, Stanford EM-X. And as you know, we will be holding them the first Monday of the month. And next one will be December 1st and then January and so on. So welcome. And we have a big year ahead of us. There's the World Cup in the USA and World Cup of electron microscopy in the UK for the first time at the International Congress on Microscopy in Liverpool next August. So I hope to see people at both events in a year's time. We have two great speakers today who's going to tell us things which will happen when the electrons go through real specimens. But before starting, I'd like to thank Yi and Jane and Prasanna for helping set us up, Jen and Professor Yi for their support, Colin and Kate and Wah as co-hosts here. And just to remind you that for the speaker questions, please pass them to us through the Q&A on the Zoom. So without further ado, I will introduce Wah, who will introduce bio speaker, has been our long tradition. Wah, please.
Okay, good morning, everyone. Welcome to our academic year's seminars to start today. It's my great pleasure to introduce Professor Werner Kühlbrandt, who is the director of Max Planck Institute of Biophysics in Frankfurt. I know Kühlbrandt decades ago. We used to stay together in Cambridge when I was on sabbatical at MRC. And Werner did a phenomenal work when he was a graduate student with Nigel Unwin at MRC to work on two-dimensional crystals by electron crystallography. And more recent year, he switched to study membrane proteins, and he has a lot of extremely exciting work that in the past years. And so today he's going to tell us his progress in cryo-electron microscopy of biological membranes and membrane proteins. Werner, welcome.
Great.
Unshared.
Thank you very much, Werner. That was fascinating. I have a couple of questions as well, but I might ask them through Colin. Anyway, I'd like to introduce Colin Ophus, who will introduce from his Edmonton connections, our next speaker, the very distinguished Ray Edgerton, who will tell us about beam damage in specimens. And Colin, over to you, please.
Sure. Thank you so much, Bob. Yeah, it's my great pleasure to welcome Professor Emeritus Ray Edgerton from the University of Alberta. Ray, you can go ahead and share your screen here. I know Ray personally, actually, from way back in the day when I took my very first TEM course. Ray was a guest lecturer, and he's one of the foremost authorities on electron-matter interaction and radiation damage in samples. He's written a couple of textbooks that are immensely important in our field, including the energy or electron energy loss spectroscopy in the electron microscope that we call the EELS Bible, and of course, physical principles of electron microscopy. He's published hundreds of amazing papers, a lot of them recently on the topic that he'll be presenting today, STEM and TEM of beam-sensitive samples. I think he's a former editor, not current, I think, for the physical sciences editor position at Micron. And then one last fun fact, I recently learned that Ray actually maintains a YouTube channel where he does MIDI synthesizer work for classical music, which I thought was totally fascinating. So I'm going through his content there. So yeah, thank you so much, Ray, for agreeing to give us a seminar today. And please feel free to take it away.
Well, thank you, Colin, for that generous introduction. I've added a letter S to the title here to indicate that nearly everything that I will say is also relevant to scanning transmission electron microscopy. And this is what a material scientist might see as evidence of radiation damage in samples. So on the left top top left. At the top on the left is a sample of quartz, and the beam is being focused in the center and gradually destroying the crystalline structure. On the top right, we have a sample of gold crystal in a high voltage electron microscope. And this time we're creating structure because vacancies that are created by the electron beam are aggregating into false structure that wasn't there originally. Then at the bottom, if you focus the electrons into a very small intense probe, you can actually drill a hole in many materials, including even amorphous carbon. And that means that atoms or molecules of the sample are going into the vacuum. That's often referred to as mass loss. And on the bottom right, you can see again for lithium compounds, which are a favorite topic for many material scientists. Again, it's quite easy to get beam damage in the form of holes in the sample. If we want to quantify radiation damage, it's convenient if the sample is crystalline, because then we can form an electron diffraction pattern and measure the intensities of diffraction spots. And on the right-hand side there at the top, this is for bacteriorhodopsin, which you saw at the beginning of the previous talk. Those numbers at the bottom of the diffraction patterns are what electron microscopists call dose, but really dose should be measured in gray units in order to compare different KV settings and compare with X-ray radiolysis. So what we actually have here is properly called fluence. It's the number of particles, electrons, per unit area of the sample. And you could see as that number increases, the intensity of the spots, particularly in the outer spot part of the pattern, decreases. Another way of quantifying the structure is through the electron energy loss spectrum. So bottom left, we have some fine structure peaks in adenine sample. They are indicative of electronic structure rather than crystallographic structure of the specimen. But once again, those peaks are fading, decreasing in intensity. And if you plot the intensity of a peak against, or the logarithm of that intensity against dose or fluence, you can see at the top, the right-hand side, you often get a straight line. And the gradient of that straight line gives us what is called the characteristic dose for damage. And the same thing with our diffraction patterns. If you take a particular spot and plot the log of the intensity versus fluence, you sometimes get a straight line. And you can see from this example that if the outer spot's fading faster, that gives us a smaller value of the characteristic dose. Mass loss can also be quantified. The simplest way would be just to time how long it takes to form a hole in the sample. But more quantitatively, you can use EELS or EDX, elemental analysis. And the plot on the right-hand side is for nitrocellulose. And you can see that when we plot the intensities of different elements, oxygen, carbon, nitrogen, they are disappearing at different rates, different characteristic dose. And that means that the composition of the sample is changing. That's something obviously that's undesirable if you want to do elemental analysis. Now, in terms of models of damage, why does it occur? This is a very simple model of the specimen in terms of just a single atom. And we have at the top here 2 primary electrons in green, and one of them is interacting with the Coulomb field of the nucleus of an atom, and that's what we call elastic scattering. That results in deflection, scattering through angles, typically tens of milliradians. But once in a while, quite rarely, in fact, you get a high angle scattering, such as 90 degrees, and that can transfer appreciable energy to an atomic nucleus. And so we can have what is called displacement damage or knock-on damage. The other kind of interaction we can have with our primary electrons is with the atomic electrons in the sample. And that gives rise to inelastic scattering, which we detect in electron energy loss spectroscopy. There, the scattering angles are even smaller, a few milliradians or fractions of a milliradian, but the energy transfer can be quite large, EV, tens of EV, even hundreds of electron volts. And the electron that caused that scattering can be ejected within the sample as a secondary electron. And that electron can also contribute to the damage by causing ionization of other atoms. And in organic materials, probably most of the damage comes from these secondary electrons. And that damage is known as radiolysis. Now, it turns out that electrically conducting specimens don't damage by radiolysis. So we're left with just the knock-on displacement damage, and that is relatively slow, but that's the only thing you would observe in a metal. Whereas insulators damage almost entirely through the ionization damage or the radiolysis. And those materials include organics and biological specimens, or zeolites, MOFs, perovskites, things that material scientists are interested in. The radiolysis occurs in stages. They're all, well, it starts off with a very fast stage, physical stage, which is the transfer of energy from our primary electrons to electrons of the sample, and then secondary electron production. That's all over within roughly a femtosecond, very fast. Then there is a physical-chemical stage where that energy gets transferred to atoms of the sample. That may take up to 1 picosecond. And that's when we start to see effects in the image or in the diffraction pattern, because there we're looking at the positions of atomic nuclei. And then that is followed by a chemical stage, which is slower and can extend even to seconds and minutes, where chemical species created by the breakage of chemical bonds, those species react with each other, they diffuse around, we have mass transport and mass loss. And for most, radiation damage can be quite an interesting topic to study, but for most electron microscopists, it's something they just want to avoid or to minimize. And so I've listed here 6 steps that can be taken to reduce radiation damage. And I'll talk about all of them, but the first 3 are the most important. And we're talking here about maximizing the signal to damage ratio, which we can do by either maximizing the signal or minimizing the damage. So item number 1 is to maximize the signal by making the image acquisition process as efficient as possible. Number 2 and number 3 and the other ones are to minimize the damage. So talking about the experimental procedure, how to optimize that, the key quantity here is something called the dose limited resolution. And I can illustrate that by this graph on the right-hand side here. If we have a sample illuminated by a beam of a fixed diameter, and that fixed diameter might correspond to a fixed resolution if we're in STEM, we have something that we can call the signal to noise ratio. The signal in this case is the change in intensity in the image as we go through a particular feature in the sample. And the noise arises from the background here. Our electrons are detected as individual particles, and therefore we have statistical noise. When we have a small number of particles, then that noise is a large fraction of the total signal. So if we plot against electron fluence, which is the number of electrons that have gone through the sample, we plot our signal to noise ratio. It starts off at 0 and remains poor where we have a small flux of electrons. Then it reaches a maximum, and the reason it does that is that we're simultaneously destroying the structure in our sample. And here in the yellow curve, I'm plotting the contrast on the assumption that that contrast behaves exponentially with dose and the characteristic dose. So beyond this point, you can show mathematically that that point corresponds to half the characteristic dose. Beyond that point, there's no point in irradiating the sample anymore because you're your signal to noise ratio is actually decreasing. You'll get a worse image. Now, if instead of plotting the signal to noise ratio for a given resolution, we plot the resolution that would correspond to a given signal to noise ratio, then we have this blue curve. And the blue curve is generated by a formula that you can see here involving various quantities that I'll discuss. D is the electron dose or electron fluence, and that fluence can be limited by many things, but the case that we're interested in is where the fluence is limited by the radiation damage of the sample. And so we can rewrite this formula here and call it a damage limited resolution. And the parameters that occur in that formula are the signal to noise ratio. And for that, we're going to take a value of 3 or 5, known as the ROSA criterion. Whether you take 3 or 5 depends on how certain you want to be that this feature that you're identifying is actually genuine. Then the quantities that occur in the denominator of this formula, the DQE is a property of our detector. It's a measure of the noise performance of the detector. F is the efficiency of our signal collection. So it's the number of collected particles, electrons maybe, divided by the number of incident particles. So F is a fraction less than 1. C is a property of the sample. It's the contrast in the sample, the Weber contrast, which is this ratio change in intensity divided by intensity. And then our final factor is this characteristic dose in the equation. And all of these quantities depend on properties of the microscope, the accelerating voltage, and also on the thickness, which it turns out to be an important parameter. And we can apply that formula to various ways of imaging in the electron microscope. And this graph is for the case of TEM bright field scattering contrast with a small 5 milliradian on-axis objective aperture. And we have a beam-sensitive organic sample. We're calculating for a critical fluence of 100 electrons per angstrom squared. And we're calculating for a feature that differs in density by 10% compared to its surroundings. And on the top right here, you can see that if we have a very thin sample, like 7 nanometers, the shaded area here represents the volume of sample that we need in order to generate an observable signal. In order to get sufficient volume for a thin sample, our width here has to be large. So the dose-limited resolution is 30 nanometers. As we increase the thickness of the sample, the dose-limited resolution gets better, smaller number. So at a thickness of about 13 nanometers in this case, we've got a dose-limited resolution equal to our thickness. And that means that the volume that describes our smallest volume that we can analyze is a cube. So if we call that a cubic voxel, this we can refer to as the voxel dose-limited resolution. Now, if we increase the sample thickness even more, then one of two things can happen, depending whether our feature, the shape of our feature in the sample. If we have a polymer with a grain boundary that runs from the top to the bottom of the sample and is parallel to electron beam, then as we increase the thickness of our sample, the signal will get larger and larger. So our dose-limited resolution will actually get better as we increase the thickness of the sample further. But many features in the sample are equiaxed, roughly spherical, or in this case, cubic. And so what happens is something different, that as we increase the thickness of the sample, the dose-limited resolution actually gets worse because this voxel scattering in that has to compete with scattering above and below the voxel. So we have two dose-limited resolutions which behave in different ways. And I think the voxel dose-limited resolution is probably the more important case, because this situation of precipitates or organelles within a cell, for example, is a more common situation. Now, also shown on this graph are the resolution limits due to chromatic aberration, important in the TEM, and beam broadening, which is something that's discussed in connection with STEM imaging, but there is an equivalent in the TEM, which is depth of field. And you can see that for this beam-sensitive specimen, those resolution limits are quite a lot less than the resolution limit imposed by the radiation damage, the dose-limited or damage-limited resolution. So particularly for thicker samples, our resolution is going to be limited by radiation damage. And thick samples are what you need in order to do tomography, three-dimensional imaging. And here on the right-hand side is a famous example of that. And by taking slices of material and illuminating the slice at different angles, we can get the three-dimensional structure with a resolution that's estimated here as 8 nanometers. Now, if we have a thick sample, how can we improve this dose-limited resolution? One way is if it's a polymer or biological sample, we can stain the sample with heavy metals. The heavy metal nuclei of the atoms cause it intense elastic scattering, and that gives us a better contrast and therefore a better dose-limited resolution. And with different amounts of stain, the resolution improves by roughly a factor of 3. These contrast measurements are from Richard Liepman's group. The other thing that we can do is change the accelerating voltage of the microscope. If we go to a high voltage microscope, it turns out that going to 1 or 3 MeV improves the dose-limited resolution by up to a factor of 3. But supposing we have a thin sample, what's the best situation? Well, we can change our imaging mode from diffraction contrast, scattering contrast, to phase contrast. And as biologists know for a long time, that gives us the best contrast and therefore the best dose-limited resolution. So here we're applying our dose-limited resolution formula to the case of this same dose-sensitive material using phase contrast in the TEM. And you'll see once again that the dose-limited resolution decreases up to a thickness where the dose-limited resolution equals the thickness. And then if we had, let's say, a boundary in the polymer or a cell wall that is perpendicular to the sample surface, parallel to the electron beam, we could in principle get higher resolution by using a thicker sample. But if we have a small equiaxed particle, a small organelle, then the resolution is going to gradually get worse as we increase the thickness. And this worsening of the resolution is because of incoherence in the scattering, which I'm assuming here is due to combined elastic and inelastic scattering. But you'll see here that we've gone from a resolution of 13 nanometers down to 3 nanometers for our phase contrast. However, from the previous talk, Dr. Kühlbrandt was talking about resolutions of angstrom units from single particle analysis. Why we're talking about nanometers here? The reason is that here we're assuming that the particle that we're detecting is unique and maybe different from all its companions. And so we don't have the luxury of averaging over thousands of particles. So the DLR that I'm describing is for a single particle in a specimen. Now, this dose-limited resolution, you can also apply it to dark field imaging. You can apply it to elemental mapping by EELS or EDX, and you can apply the same principle, the same definition to X-ray imaging, either absorption contrast or phase contrast X-ray imaging. So this single parameter combines the properties of the radiation, the sample, the imaging procedure, and the performance of our detection system. So that's what I want to say about improving the efficiency of the signal collection, the image acquisition. If we go on to talk about minimizing the damage, one of the ways that's commonly done is to cool the sample. This is quite effective for organic samples. You can get a factor of 10, sometimes greater, by cooling. Recently, people have tried using liquid helium cooling. The results have been variable, but these recent results from Cambridge give something like a factor of 1.5 up to 2 by going from liquid nitrogen temperature down towards liquid helium temperature. Another thing you can do is to encapsulate the specimen in some way. Here are single atoms, atomic clusters encapsulated in a carbon nanotube, keeping the atoms in place. Graphene layers have also been used to prevent atomic motion with appreciable protection factors. And earlier work over many years has shown that if you use evaporated coatings, which can be carbon or metal, that prevents or reduces the amount of damage, either mass loss or crystallographic damage by an appreciable factor. Of course, it also may reduce the contrast, so that is reducing the dose-limited resolution, and that has to be taken into account as well. Elemental substitution, replacing hydrogen by a halogen, for example, makes the material a bit more radiation resistant. Even replacing hydrogen by deuterium gives us a useful isotope effect. Scavengers are chemicals that reduce damage when you have aqueous systems, but for the solid samples that we use in the TEM, the results of using scavengers has been very controversial and minimal. So it's really not a useful general procedure. Dose rate effects occur. I've assumed up to now that the characteristic dose is independent of the dose rate, but some measurements show that it's not, and we can have either an inverse dose rate effect where the characteristic dose increases with dose rate, or a direct dose rate effect where it decreases, the material becomes more sensitive. A famous example of this inverse dose rate effect is the X-ray free electron laser, where with the intense amount of photons, 10 to the 12, that you can put on a sample within only 50 femtoseconds, you can actually read out a diffraction pattern within 50 femtosecond time scale before the sample has had time to damage. Unfortunately, that's not going to happen with electrons. For one thing, our dose rates, even for a cold field emission gun, are a factor of 10 to the 5, 10 to the 6, lower than for the XFEL laser system. And one reason for that is that coulombs, the electrons repel each other by Coulomb repulsion. And so we can't get anything like this number of electrons within a single pulse. Up to now, I've assumed in those formulas that this characteristic dose is just a constant dependent on the material, but in fact, that characteristic dose is observed to be dependent on the spatial resolution. That's the reason why the outer spots in the diffraction pattern fade more rapidly than the inner spots. And here are data for bacteriorhodopsin from several workers, different temperatures. And if you plot this characteristic dose versus the despacing corresponding to those straight plots, you get a straight line, implying that this characteristic dose is proportional to resolution or despacing to the power of 1. Some X-ray measurements imply that for really good resolution, small d, that this exponent is closer to 2. And I suspect that in principle, that exponent depends on resolution, changes from 2 to 1 upon root 2 as you change the resolution. And all of that can be incorporated into that dose-limited resolution formula. And it means that the voxel dose-limited resolution, for example, goes as characteristic dose to the 1/5 power rather than to the 1/4 power. It's interesting, I think, to compare radiolysis due to electrons with radiolysis due to electrons. And this graph here is a modification of one published by Howells some years ago. He plotted the required dose for adequate statistics against resolution, and also the dose that gives damage, and where those two intersect is what we've been calling dose-limited resolution. So I've added to that plot a second required dose line for electrons, based on the fact that, according to calculations of Henderson many years ago, electrons have a much larger scattering elastic cross-section than X-rays, and so this line is a factor of 1,000 lower. And so you'll see here where our data intersects the line, we've got a dose-limited resolution that's roughly a factor of 10 better than for X-rays. The other thing that we can see from this plot is that X-ray data in blue and electron data correspond to roughly the same characteristic dose for these different resolutions. And so we can say, to a first approximation, the characteristic dose is the same for electrons and X-rays. Not that surprising, because we're talking about the same radiolysis process in both cases. However, when you look at the temperature dependence of this characteristic dose, it tends to be higher for X-rays compared to electrons. So the characteristic dose can only be the same for one particular sample temperature. And I suspect that's going to correspond to a low temperature, and that at higher temperature, the characteristic dose for X-rays is probably going to be smaller, because we're talking about chemical damage, which might be more extensive in a thicker sample, which you often find in the X-ray situation. Other differences between X-rays and electrons have to do with the localization of the damage. For electrons, you can do calculations, measurements that show that the initial transfer of energy from the primary electron takes place within a radius of roughly 1 or 2 nanometers, whereas X-rays produce their damage by exciting photoelectrons or Auger electrons. And those Auger electrons have an appreciable range because their energy can be hundreds of electron volts. So for X-rays, the initial localization of the damage is on a larger scale, a scale of tens of nanometers or even hundreds of nanometers. And so these differences between electrons and X-rays, I think, might tell us something about the mechanisms of radiolysis in both, for both X-rays and electrons. And that also, that localization of the damage is relevant to damage due to pulsed beams. XFEL has shown us that there's a possibility of reducing damage. People have been trying with electron beams, and some positive results have been obtained, but they are hard to understand, and they have been recently disputed. So more experiments are needed with pulsed beams. Also, in the case of the stem, that's a dynamic situation, and many parameters are involved, including the dwell time, the scan pattern, and there are indications from experiments that many of these parameters are important in determining the damage. So just in summary, the most effective thing you can do to reduce radiation damage is to optimize your imaging conditions. Choose the best method for imaging and the best instrumentation, including the KV and the detector. Dose-limited resolution is a useful parameter for measuring damage. It tends to have values in the range 3 to 30 nanometers, not angstrom units for a beam-sensitive specimen. Cooling encapsulation are useful measures to reduce the radiolysis, and comparing radiolysis of electrons and X-rays by either calculations or experiments, I think, might provide us greater insight into the radiolysis mechanism and maybe even suggest situations that can minimize the damage. So that's what I wanted to say. Thank you.
Thank you so much, Ray, for an excellent overview here. And I always learn new things every time I see you give a damage talk here. So I would like to invite the audience to ask questions. Please use the Q&A panel. Feel free to type a question, and I'd be happy to read it out and get Ray's thoughts on it. And of course, panel 2, welcome to ask questions. So maybe while the audience is typing questions, Ray, I have a question that occurred to me. Like, I've been looking at the dose-limited resolution formulae for X-ray, for EDX, in particular for chemistry, right? What about for correlated experiments? Like, if I have simultaneously the X-ray measurement and the HADAF measurement, and I'm doing kind of a weighted sum, right, to use the high signal to noise of the HADAF and then get the chemistry from the X-ray, sensor fusion, basically, how would I modify that formula, do you think, to take into account correlative imaging?
You're talking about generalizing to do X-ray detection and EDX.
And imaging, yeah, like EDX and imaging, let's say,
Right.
or EELs and imaging.
The factor F in the equation, which is the efficiency of signal collection, is going to be a lot less for EDX, because that F is the ratio of the number of X-ray photons to the number of incident electrons. And that is determined mainly by the cross-section for ionization, but also the detector efficiency, the collection angle of the X-ray detector. So all of that can be included into the formula. And when you do that, you get values of the order of 10 to tens of nanometers, typically for the dose-limited resolution for EDX mapping. And the same for EELs. It depends on the atomic numbers involved, whether the EELs or the EDX is more efficient at analyzing a beam-sensitive specimen.
Okay, let me read the first audience question here. So are there any methods to quantify the radiation damage in different materials with high precision? And for example, could you predict chemistry, like for example, formation of nanodiamonds due to radiolysis of adamantane, as per a recent report, although I haven't seen that report?
Yeah, well, precision is not something you tend to find in radiation damage measurements. For various reasons, there's often a lot of scatter in the data that gives you this characteristic dose. So you try your best, and particularly for beam-sensitive materials, very beam-sensitive ones, it's difficult to get accuracy. Inorganic materials, I've talked mainly about organic materials because they are of great interest to biologists. Inorganic materials are in general more complicated because inorganic materials can have very different structures, and the mechanism, even if it's a radiolysis type of mechanism, can be different in different materials. It certainly would be nice to be able to do calculations of radiolysis, and so far those calculations are not really very realistic. People have tried to do quantum calculations of the initial stage of damage, and using sophisticated methods, they can calculate what's going on at the atomic molecular level in the primary stage of damage. But that's only the first stage in the damage, and that gives you results that are temperature independent, which is not the real case. So radiolysis being quite a complicated process, it is going to be a difficult problem to calculate, and I would say progress is slow.
Yeah, I can't even imagine how to calculate secondary mechanisms, let alone tertiary, in any realistic time scale. Yeah, you're totally right about that.
Well, people have tried to calculate the later stages of damage in terms of diffusion mechanisms.
Yeah, yeah, empirical models for sure. I think it's possible, but a first principles model, I think, is still out of reach. Yeah. So, do we have any other questions from the panel or from the audience for Ray here?
I think there's a question about liquid helium versus as a coolant. Liquid helium as a coolant. It's a question on the Q&A, I believe.
Yeah, sorry, that's higher up. Yeah, so does liquid helium reduce radiation damage because it ice at low temperatures in a different state, or is it a pure temperature effect, I think is the question.
Well, there have been a lot of non-consistent results from using liquid helium. And I think the reason is that the liquid helium causes all kinds of other effects, maybe including ice formation. You can deal with that by having a very good vacuum, but there are other things that happen. There may be phase changes in the sample. The sample may become very insulating and charge up in the beam. And so I think until recently, there's been no consensus about the effect of liquid helium. I tend to believe those results from the LMB group in Cambridge, which say that the improvement is a factor of 1.5 to 2, typically for the organic materials that they're interested in. That sounds like a small factor, but for them, it's an important factor for the single particle analysis.
Yeah, that's true. Okay, so other questions?
Let me just interject. Actually, we did experiment decades ago on liquid helium. We find approximately 1.4, 1.5 at high resolution spacings. But for lower resolution data, that's actually a big gain. So it depends on what is after. If you're after 2 angstrom resolutions, you get maybe very small gain in liquid helium. But if you're after 10 angstrom resolution, I mean, that will be a bigger gain. I mean, we published those data in Journal Microscopy years ago.
Yes.
Compare liquid helium and nitrogens.
Okay, another question here. Are there any techniques to mitigate beam-induced carbon contamination other than plasma cleaning and beam showering? Any ideas, Ray?
Lots of things have been tried, including low energy electrons on the sample, which I think is a technique that is used in surface science, UHV equipment. Plasma cleaners. You want to clean the sample without damaging the sample. Yeah. I think that is the problem.
The trick. Yeah.
You can use vapors, you can use plasmas, but if you have particularly an organic sample, that may be damaged by the material. So obviously, good vacuum is important, and the vacuum in microscopes has been improving gradually over the decades.
Yeah, something to try in the ultra-high vacuum microscopes. Another question, for increasing critical dose with cryo temperatures, do we have a sort of an idea why some materials show much greater increases or decreases than others? Like what is the fundamental reasons? Do you have any theories, or are there any theories for it?
Well, I think the reason that the critical dose changes with temperature has to do with the later stages of the damage, and they involve diffusion, chemical reactions, and those reactions are going to be different with different compounds. So it depends on the chemistry of the material, how stable it is, how easily its components can react when they are turned into something else by the beam.
Yeah, that's a good point. Kate, you have a question?
Yeah, thank you, Ray, for the excellent talk. I really, really enjoyed it. I had a question on the encapsulation mechanism for limiting damage. So the first part of the question is there some way to calculate, what thickness of encapsulant will give you the best trade-off between like minimizing your damage, but also keeping a good resolution? And the second part to that question is I've seen people get quite good results by encapsulating materials in hexagonal boron nitride or HBN, which would be unusual to me because that's an insulator. So I would think maybe it wouldn't conduct away stuff as good as something else. So I was curious within the mechanisms why you think, those type of insulating encapsulants work quite well.
Well, and people seem to get good results from graphene, although I think there's a lot more work to be done. And graphene supposedly is impermeable to everything except, I think, hydrogen. So it's easy to understand why graphene might prevent mass loss from the sample. But the information experiments over the ages has shown that not only the mass loss, but the crystallinity of the sample is better with a layer on the surface. And people have tried to work out, does it have to be a conducting layer? Does a conducting layer add electrons, make it more like a metal? And I had a list there of all of the mechanisms, maybe half a dozen in number, that have been proposed as to understand this protection effect. Obviously, in order to stop reducing the contrast of the sample too much, you want to have your encapsulation layer as thin as possible, but that may make it less effective as an encapsulant. I don't know really the answer to your question. I think more work needs to be done, but there is, I think, sufficient evidence that encapsulation really does work in a variety of situations, maybe not in every situation. And graphene looks like a promising candidate to me.
Very much so. Bob is unmuting, so I think that means our time is up. Bob?
I was just going to ask Ray an anecdotal question, which is we found that our cross-section iron milled samples survived remarkably well for high resolution in situ imaging over periods of time. And I'm wondering if the surface damage induced by iron beam milling, which we often thought was creating a small thin layer on both sides, and then encapsulating and allowing the real thing to be studied at quite high resolution. Now that's just anecdotal. We've never proved it, but even the iron beam damage might help in that regard.
Yeah, well, I remember a talk by Richard Liebman in your EM-X series, I think a year ago, where he talked about the effect of gallium, if it is implanted in the material, can actually make it less sensitive.
Yeah, that was an interesting point. I forgot about that one. Okay, let's take one last quick question and then we can wrap it up because it's 9:30 here. The question from Vinayak over at Northwestern is, how about the damage situation in dilute systems like gas phase imaging, and can damage be minimized or tailored in some way?
I'm not sure what is a dilute system.
Like a gas cell
open
or
structure? I think there's plenty of evidence that as you go from a compact solid to an open solid, that the material gets more radiation sensitive, zeolite being a good example. And that's probably understandable because you have atoms which are next to a void, essentially, or a channel, and they're less strongly bound. That would be a kind of hand-waving answer.
Okay. Yeah, no, thank you so much, Ray. And I think in the interest of ending on time here, we should probably wrap it up and really thank both speakers again for giving such excellent talks. And I quite enjoyed the discussion too here. So thank you so much, Werner and Ray, for giving us your time here at EM-X. We really appreciate it. Bob, any last words?
Yes, that's Wa. Do you have anything to say? And then I'll wrap up.
Yeah, no, I think both talks are excellent. And Ray, thanks very much your account on explaining what radiation damage means to the general audience. And we definitely look forward reading some of your papers. And actually, there's one more radiation damage questions I think related to maybe to Werner. The question is in the glutamic 111. Have you investigated its radiation damage effect? No, you need to unmute. Yes.
Phone is. Can you hear me now? All right. So no, we haven't. I think as far as we can see, all glutamates are damaged to the same way. Some are damaged less, probably because of their chemical environment. But these 10 glutamates in the ring, they some of them are better defined than others. But that must just be sort of noise or random effects. I don't think they would suffer different rates of damage. It's just because chemically they're all the same, and it's just at the edge, from the in principle you can tell from the density of the side chain whether it's damaged or not. But then it's I say there's noise as well, so we haven't. I wouldn't I wouldn't bank on being able to tell from the experimental density, map density, whether the side chain is damaged or not. And it's so I don't think we can tell, basically.
Well,
Let me just comment. I think in principle, I think one can quantify the amount of damage by additional data analysis. But that's quite a bit of work. I mean, you can analyze basically
Yeah.
every residues, what dose you get damaged. But there is some work, I think, still ongoing in some labs as well.
Well, in principle, you can also extrapolate to 0 dose. You know, this is what was been done in one example for upper ferritin, I think. So that is, and then you can extrapolate to 0 dose, and then you get the real density. But we haven't really gone that way. It would be a tremendous.
So I suggest that we carry on this conversation online now. But we should bring the session formally to a close and thank our speakers, which were 2 terrific talks to get us off to a new year. That we will have our next on the first Monday of December, which is right after the American Thanksgiving. And we can stop the recording, but anyone can stay online and ask questions through Q&A and talk to the speakers as necessary as we wind down. But we can stop the recording now, and thank you very much and see you in December.
Thank you.
Thank you.
The recording is stopped.